Hello everyone, welcome back to Aerominds Training Center. So in the last video we did chapter 3 which is temperature, and now we are starting with chapter 4 which is density. So before we touch the formulas, numbers or exam topics, I want you to understand a very important thing. Air density is not just a theory chapter. It directly decides whether your aircraft will struggle or perform very comfortably. Now, it decides how long a runway you will need, and how fast you must fly, and how well your engines are breathing, basically. So, your how safely you can climb, and how safely you can climb after takeoff. So, this chapter quietly connects meteorology, performance, navigation, and real life flying. Okay, so as we go on, we'll start with the importance of density in aviation. So air density simply means how thick or thin the air is. Okay, that is it. How thick or thin the air is. Okay, now imagine air like a crowd of people. Okay, if the crowd is lightly packed, that is dense air. And if the people are spread far apart, that is low density air. So it will be like this. Suppose this is an area and people are standing like this. So these are closely packed. But if it is there is an area and people are standing like this, so it is a less dense area or a less dense parcel of air. Now, why aircraft loves dense air is because everything an aircraft does, it depends on pushing air. The propellers of the aircraft are pushing the air backward. Okay, so everything depends upon pushing the air, breathing the air, and using the air, basically. Now, now the lift which the aircraft is generating depends upon the air molecules which are hitting the wing of the aircraft. Now, if we talk about the engine thrust, so the engine thrust depends on how much oxygen is entering the engine. Propellers depend on air to push backward, and even brakes and the landing performance are indirectly affected by air density. Now, that is why air density is a critical factor. It is a critical factor for aviation. It is not optional, not secondary, it is very critical. Now let us slowly understand the effects of uh, low density air on aircraft performance. Now first is slower climb rates. Now when air density, so density is denoted by this, which is called rho. Now if the air density is low, okay, the air molecules will be very less, molecules will be less. Now the wing produces the same lift at the will produce less lift at the same speed. Okay, the engines produce less thrust because it is breathing less oxygen. Okay, and so when the aircraft tries to climb, it feels heavy. When it is trying to climb, it will feel heavy and somewhat lazy, if you can say. The climb angle will reduce of the climb angle of the aircraft will reduce. And even if you pull the nose up, the aircraft will not climb very well. And in exam, remember this logic. Lower the density means poor climb rate. Okay, lower the density, poorer the climb rate. Now the second is higher landing and takeoff speeds required. Now this is extremely important because the lift is depending upon the air density, and if the density is low, the wing must move faster through the air to generate the same amount of lift. Got it? Now that means higher TAS will be required for takeoff. TAS is true air speed. True air speed. TAS is true airspeed. So higher TAS will be required for the takeoff roll. Then on landing also you must approach at a higher speed. When you are coming for landing, you have to approach at a higher speed. Suppose your approach speed is 100, you have to approach at 110 knots. So low density means higher speeds. Now in DGCA questions, they may ask you indirectly what happens to the takeoff speed when the density reduces. So what happens? The answer will be the takeoff speeds increases. Remember this. Okay. So we'll mark um, air density is a critical factor in aviation, significantly impacting the aircraft's performance. Got it? Now, effects of low air density on aircraft performance. First is the slower climb rate, which I told you. The aircraft will not climb much and it will feel lazy. Then the second is higher landing and takeoff speeds required. And why is it required if someone asks you? Because for the same amount of lift, you have to increase your speed. So that is the answer. Then comes the third one, which is reducing the engine thrust. Now, engines are basically like lungs. So they are breathing the air inside. Now, when air density is low, first we'll see engine is like lungs, and when air density is low, what happens? Oxygen content per unit volume reduces. Okay, now less oxygen means combustion less combustion. Okay, then if there is less combustion, what will happen? Less combustion means less power. Okay, this applies to piston engines as well as your jet engines. Okay, so the engine cannot give its full rated power. That is so now this is why hot and high airports are performance critical. Okay, so we'll see reduced engine thrust. Now, next is longer runways are needed for both takeoff and landing. Now, why is it so? Now, combining everything we just discussed, higher speeds are required. Now, acceleration is slower because thrust is reduced. As we saw, thrust is reduced, so the acceleration will be slower. Okay, now the because of this, the climb rate will be poor and the stopping distance will increase because your speed was also increased. Now, if the runway is short and density is low, what will happen? You are basically inviting danger to yourself. So this is why performance calculations are very mandatory before every flight. Now, before moving to planning implications, we'll mark this quickly. Longer runways are needed. Now, if anyone asks you why, so you have the answer. Because at low density, at higher airports, uh, what happens? Engine thrust will be less produced and the climb rate will be less and landing speed will be more. So, you're basically inviting danger. Now comes the planning implication. Now, this is where the actual theory meets your actual flying. So aircraft takeoff and landing distance must account for the density effects. It is written. Now you cannot assume the sea level performance at a high station hill station. Okay, or in basically summer afternoons with high temperatures. So the performance chart already assume a certain density conditions. Okay, now as a pilot, you must calculate the density altitude and then check whether the runway length is sufficient or not. Suppose your runway, uh, your density altitude is 10,000 feet, and at this, the runway length required for your landing is 2,000 meters, but the runway is only 1,500 meters, so you cannot land at this runway. Okay, so now next is all up weight calculations must be adjusted. Now if the density is low, you cannot carry full weight. Okay, you may need to offload some of the passengers or some of the fuel basically or the cargo. Now this is very common in commercial operations. Okay, now weight that is safe in winter mornings may be unsafe in the summer afternoons. You can take it like that. Now DGCA loves asking these questions, which are connecting to the density altitude and the maximum takeoff weight. Okay, so remember this: aircraft takeoff and landing distance must account for density effects. Then aircraft all up weight calculation must be adjusted. It should not exceed. Then comes your definitions and units. So atmospheric density is denoted by the symbol rho, as I told you. Rho. It is defined as atmospheric density is the mass of air contained in a unit volume. Contained in a unit volume. mass of air contained in a unit volume. Remember this. Okay. Now, a very simple meaning of this is how much air weight is present inside a given space. Suppose you have a tiffin box and you have air inside it, not food. So, how much air is present in that will give you your density of that tiffin. Now, more mass in the same volume means higher density. Okay, less mass means lower density. Got it? Now the units are gram per meter cube or kilogram per cubic meter. In aviation, we usually use kilograms per cubic meter. Okay, so atmospheric density is defined as rho. Uh, it is denoted as rho and defined as the mass of air contained in unit volume, and the units are gram per cubic meter or kilogram per cubic meter. Now comes the very important term, which is density altitude. Now listen to this carefully. Density altitude is not actually a physical altitude, it is just a performance altitude, not a physical altitude. Remember this, it is not a physical altitude, it is a performance altitude. Very important. Now, density altitude may be defined as the altitude above the mean sea level at which a given atmospheric density occurs in the international standard atmosphere. Okay, now if I simplify this, density altitude answers one question: at what height in the ISA, ISA is International Standard Atmosphere, in the ISA would I find the air with the same density as my current air? Okay, that is it. Now, if you are standing at an airport, suppose at 2000 feet, okay, but the air behaves like air is at 5000 feet, then your density altitude will be 5000 feet. Remember this. Got it? Now, so the altitude above mean sea level at which given atmospheric density occurs in the international standard atmosphere. Now you can remember the example which I have told you. Suppose you're standing at 2000 and then you feel the air is at 5000, so the density altitude will be 5000. Then comes the ISA relationship. So, aircraft performance cares about the density altitude and not your actual altitude. Okay, suppose your aircraft is standing at a altitude of 1000 feet, but the air which is it feeling, it will be 6 or 7000 feet, so the density is reduced. Okay, so the aircraft performance will be degraded. So that is why aircraft needs to know what is the density altitude. Now if we see the ISA relationship, what it says is in the international standard atmosphere the pressure altitude is equal to the density altitude. Now why? Because ISA assumes a standard temperature, no deviations at all, and so density depends only on pressure, as we saw. So hence the pressure altitude equals the density altitude where in the ISA. Remember this. So in ISA, pressure altitude is equal to the density altitude. Okay. Now comes a very favorite exam rule, that is temperature deviation rule. Okay. Now a 1 degree Celsius deviation from ISA is equal to 120 feet change in the density altitude. Remember this. 1 degrees Celsius deviation is equal to 120 feet change in the density altitude. Remember this. Okay. Then, so this is the thumb rule. Not an exact equation, but DGC heavily uses it. Now, if the temperature is higher than ISA, okay, what will happen? The density altitude becomes higher than the pressure altitude if the temperature is more. Why? Because the warmer air will expand. Warmer air expands and cold air contracts. It was told in chapter 2, which is atmospheric pressure. So warm air expands and expanding air is less dense. So less dense air behaves like the air is at a higher altitude. Okay, so remember this golden logic. Hot air equals high density altitude, and a warmer atmosphere than ISA results in a higher density altitude always, no matter what. Okay, now the operational impact. So high density altitude means takeoff and landing occurs at a higher effective altitude. So what it means, basically, the higher density altitude means takeoff or landing occurs at a higher effective altitude. Even if your altimeter is saying that 2000 feet, the aircraft will feel like it is at 6000 feet. Now the engines, the wings and propellers, everything, they all behave according to that, which is the 6000. Okay, so remember all this. The deviation is 1 degree Celsius from ISA, 120 feet change in the density altitude. Then, if the temperature is more than ISA, the density altitude will be more than the pressure altitude. So, temperature more, more expansion, and the altitude, density altitude will rise up. Then comes a warmer atmosphere in ISA results in a higher density altitude. It is same as this line. Then comes the operational impact, which is high density altitude means takeoff and landing occurs at a higher effective altitude. Then comes the now we are moving to density of dry air. Okay, PV is equal to nRT. So this is where the formula comes, but I'll explain very slowly. So density of dry air is actually calculated using a fundamental gas equation. Okay, now the fundamental gas equation is PV is equal to RT. Now P is the pressure, then V is the volume, R is a constant, and T is the temperature, absolute temperature. It is the absolute temperature. So this equation applies to gases, and it is including air. It also applies to air. Now the derivation for density is mass divided by volume. Now for unit mass, density becomes the reciprocal of volume. So if we rearrange the equation, P divided by rho equals RT. P divided by rho equals RT. That gives rho equals P divided by RT. Okay, now this is a very important exam result. The density equals the pressure divided by the temperature. So if the pressure is increasing, the density is increasing. If the temperature is increasing, the density is decreasing. Now this explains most of the aviation behavior. Okay, now let us understand the symbols clearly. So P is pressure and it is measured in hectopascals, HPA. Remember this. And mean sea level pressure is 1013.25 hectopascals. Go, this is it. Then comes R, which is the gas constant for a particular gas. And for dry air, it will have a fixed value. Now, that is not more important. You just need to know uh, from the surface level. Now comes T, which is absolute temperature. So absolute temperature is in Kelvin. So K stands for Kelvin, and it is always in Kelvin. It is never in Celsius or Fahrenheit. And V is the volume, as we know. Now, if we see a ISA surface condition example, now the now the gas constant for dry air is given 2.87 multiplied by 10 is to the power 3. Now, ISA surface pressure is 1013.25 hectopascals, and ISA temperature is 15 degrees Celsius. Now, if you want to calculate it, when you put these values into equation, the density comes out to be 1.225 kilograms per 1.1225 grams per meter cube. And if you want to convert it into kilogram, that is 1225 kilogram per meter cube. Now this is a very this value is very important for your exam. Now DGC expects you to remember this ISA sea level density value. Okay, so by putting in these values in the formula, you will get the value for the density. You guys can put it in this. So rho is equal to P upon R T. Now we'll mark what is important. So the density of dry air is calculated by a fundamental gas equation. Remember this equation: PV is equal to RT, and the derivation for the density will be this. So P is equal, rho is equal to P upon RT, where these are the names for the symbols, and then temperature is in Kelvin, then volume. Now comes the example. So suppose the gas constant is this, the pressure is given as this, and temperature is this. So you guys can find your density, which is the mean sea level density. Now we move to the density of moist air. So previously we did was for dry air. Now we come to the moist air. Now water vapor is also a gas, if you see. So it also obeys the gas law. It will obey the gas law. Now the gas constant for water vapor is 8 by 5 times that of dry air. Now that means that means water vapor behaves differently, somewhat differently from the dry air. Now total pressure of the moist air, which is pressure total, uh, equals the pressure of dry air plus the pressure of water vapor. So the total pressure equals P plus E, where E is the vapor pressure, water vapor pressure, and P is the dry air pressure. Okay, now comes the density components. So density of water vapor equals 5E divided by 8 RT. Okay, and density of dry air equals P minus E divided by RT. And when we combine these both, we'll get density of the moist air equals P minus 3E divided by 8 divided by RT. Okay, now here comes the key takeaway, which is, and now this is important, remember this: moist air is less dense than dry air under similar conditions. um, Many students think that humid air is heavy, and that is completely wrong in aviation physics, because water vapor molecules are lighter than oxygen and nitrogen, which combine for 99% of the atmosphere. Now when water vapor replaces dry air, overall density will decrease. Now humidity's effect on density is small and often ignored in general aviation, but DGCA can test your knowledge with this. So remember, hot air and hot air and high altitude, and humid air, all these reduce the density. Okay, hot air, high altitude, and humid air, these reduce the density. Okay, and reduced density means lower will be your aircraft's performance. So that is it for this equation. So density of moist air, water vapor as gas also obeys the gas law, and gas constant for water vapor is 8 upon 5 times that of dry air. Now comes the total pressure for moist air, which is P plus E, which is dry air plus water vapor. Then comes the density components, and then comes the final equation. So remember the final equation for your exam. Then comes the takeaway, which is moist air is less dense than the dry air under the similar conditions. Now, however, the density's effect on the humidity's effect on density is small, but and it is often ignored in aviation. But you can be asked it in your exam. Now we'll move ahead and talk about the factors which are affecting your density. Now, air density does not always remain constant, as we know, so it keeps changing. It changes with height, with temperature, and with moisture in the air. Now, if you understand all these three, you'll understand almost entire of the chapter. So first factor is altitude. Okay, altitude. So as altitude increases, it says the air density decreases. Altitude increases, density decreases. Now I hope you know this, but if I explain it to you again, so near the surface of your earth, air is pressed down, okay, due to the static pressure. by the weight of the air above it. Okay. Now, so the air is tightly squeezed near the surface. Okay. Now, whenever you go higher, what happens? The air becomes more spread out. Okay. Spread out means very fewer air molecules are in the same space. Now, if you imagine this column and you're flying from here to here, now here the density will be like this. But as you move upward, it becomes very less. Okay. So, fewer molecules mean less density. So, very simply put, higher altitude means thinner the air. And thinner air means lower density, where and lower density means the poorer aircraft's performance. That is it for this. So remember the explanation and the point. So altitude increases, density decreases, and now you know why this happens. So when you find the this question in your MCQs, do tick the air density will decrease with increase in altitude. Next comes the temperature increases, air density decreases. Okay. So why does this happen? When air is heated, the molecule starts moving faster, and when they move faster, they move away from each other. That is it. Now, this increases your volume of the parcel, but the same amount of air, and the larger the volume, what will happen? Your density will reduce. Okay. Then comes, so temperature increases, density will reduce. Remember this. Now, so air, so the warm air is lighter as compared to cold air. Okay, now this is why early morning flights perform better than the afternoon flights, especially in the summer. So if you are also flying on your own, if you see your takeoffs or your climb performance in the winters, or in wintry mornings as compared to hot summers in the afternoon, your winter climb will be better than your summer climbs. Okay. Now third factor is humidity. So humidity means basically the moisture content, moisture or the water vapor which is present in the air. Okay, so humid air is lighter, which means it is less dense. Humid air is lighter, which means it is less dense. Now, this sounds confusing at first because many people think that moisture means heavy air. Okay, but in physics, the water vapor molecules are lighter than oxygen and nitrogen molecules. Then water vapor replaces the dry air, which overall reduces the density. So I told you previously also. Now comes the another important topic, which is high temperature allows air to retain more water vapor. Now warm air can hold more moisture. So hot and humid conditions are worst combination for the aircraft's performance, especially climb. Now an operational tip, remember, and it is very practical also. So if humidity is high, add 10% to the computed takeoff distance. This is not a law, it is a safety margin kind of thing, which is used in operations, because humid air reduces your density slightly, and that slightly reduced density can increase your takeoff distance and reduce your climb performance. So, and also expect reduced climb rate in humid conditions, not dramatically reduced but noticeably reduced. Okay. We'll mark humidity. Humid air is lighter because it is less dense. Okay. Then higher temperature, more water vapor can be retained. Got it? So, and then comes the operational tip. Add 10% to the computed takeoff distance if the humidity is high, and expect a reduced climb rate. Got it? So when the humidity increases, the density will reduce. Then comes the variations in the surface density. Now, surface density basically means the air density which is near the ground, as it says. The name suggests surface density, so it is near the surface, near the ground. Now, first is the temperature dependence. Now, at a given pressure, density will be inversely proportional to the absolute temperature. So what this means is that density varies as 1 divided by temperature in Kelvin. Okay, 1 divided by temperature, which is in Kelvin. So if the temperature goes up, the density will go down, and if the temperature goes down, the density will go up. Now again, The warmer air is lighter and cold air is heavier. Warm air is light and cold air is heavy. Remember this. Okay. Now we'll talk about the diurnal variation. So diurnal basically means daily variation. Lowest density is in the afternoon and highest density is just after the sunrise. Now, why is it lowest in the afternoon? Because the ground heats up during the day. The temperature rises and heating the air near the surface. The earth heats the air which is near the surface. Okay. And why is it highest density at after the sunrise? Because during the night the earth allows some cooling and the cold air settles near the surface, which makes it very dense. Now this is why the performance charts are often assume early morning conditions, if you have noticed, for the best performance. Now comes the seasonal variation. So seasonal variation, basically density changes across seasons due to the change in temperature and pressure. Temperature and pressure changes every season. Now in winter, if you see, the air is colder and it is denser also, and in summer the air is warmer and less dense. Now the pressure pattern, if you remember, also changes with seasons, which affect the density further. Okay, then so we'll mark what we saw. At a given pressure, density is inversely proportional to the temperature. So warmer the air, the lighter will be the air, and colder air will be heavier. So density varies according to that. Then comes the diurnal variation. So lowest density will be in the afternoon, highest density will be just after the sunrise. So remember both of these. It is also for your CPL training also, you will be asked this. Then comes your seasonal variation. So due to changes in temperature and pressure across season, the density changes. Now let us look at the approximate density values uh, for the density. Now 1% decrease in density is caused by one of the following, which can be a 10 hectopascal fall in the pressure, or a 3-degree rise in the temperature, or a 300-foot increase in height. Okay, this is not exact physics. These are rule of thumb values used for quick estimations basically. And DGCA may ask these directly or indirectly in your MCQs. So remember these values. A 1% decrease in density may be caused by 10 hectopascal fall in pressure, 3-degree rise in temperature, and 300 feet increase in the height. Height increases, density decreases, pressure decreases, density decreases, and temperature increases, density decreases. That is it. Now we move to variation of density with height. So in the international standard atmosphere, the density decreases with height at all levels. Okay, there's a complete value chart in which it says density reduces with height at all levels. There are particular levels: 10,000, 20,000, 30,000, and every other level has a reduction in density as we go up. So what happens, there is no level where the density increases as you go up, it will only reduce. Remember this. Now for a lower level approximation, if you see, for every 1000 feet increase in the height, density decreases by about 3% of its value. Okay, and this approximation is valid up to about 20,000 feet only, and beyond that the rate changes, and this simple rule becomes inaccurate if you see. Now comes the atmospheric extent. Now it is a very interesting concept. So first we'll mark this variation of density with height. So density decreases with height at all levels. Remember this. Lower level approximation is that up to 20,000 feet, for every 3,000 feet, 1,000 feet, there will be decrease in density by a value of 3%, and valid up to only 20,000. Remember this. Now comes the atmospheric extent. So if you see, the density remained constant like it is at the surface. Okay, the atmosphere would end at about only 3 kilometers. That means the air would suddenly stop, but that does not happen. because the density reduces gradually as we go up, and the atmosphere extend up to 500 approximate 500 kilometers, 480 kilometers. Now we'll look at some numbers. At 6 kilometers the density is about half of the surface density. Okay. And at 11 kilometers density is about one quarter of the surface density, and 17 kilometers density is about one tenth of the surface density, one eighth of the surface density. And even at 240 kilometers there is still enough air density to create a resistance for the space aircraft. Okay. Then now that is why the satellites slowly lose their speed and need correction burns. Okay. So we say the atmosphere extends up to 800 kilometers, and not because the air is dense there, but because air molecules are still existing there. Okay. So remember these values. If the density will remain constant, the atmosphere will end at around 8 kilometers only. It will not be extended up to 800. Then at for 6 kilometers, density will become half. For 11 kilometers, one fourth. And then for 17 kilometers, it will become one eighth. Remember this. And even at 240 kilometers, there is enough density to resist the spacecraft. And then comes the latitudinal variation. So latitude basically means the distance from the equator towards the pole. So this is the equator, and this will be the pole, and this is the surface of the earth. So as we go from here to here, the latitude increases, so latitudinal variation. Okay. Now at sea level the density will be lowest at the equator and highest at the poles, up to about 8 kilometers only. Remember this. Lowest at the equator, density will be lowest at equator, and density will be highest at poles, at sea level only. Okay. And up to 8 kilometers. Now if you ask why, because equator as we know is hotter, and hot air expands because and becomes less dense. The poles are cold, so the air is dense. And above 8 kilometers something interesting happens. Now what happens, there is a reversal. Now density becomes higher near the equator than near the poles. This happens because the atmosphere is thicker over equator. Okay. Which is due to expansion and heating. So at higher altitude there is more air over the equator compared to the poles. Okay. Now that is it for this. So density lowest at equator, highest at poles. So remember, at sea level lowest at equator, highest at poles. Why? Due to the temperature. But after 8 kilometers, the density becomes higher near the equator than the poles after 8 kilometers. Remember this. It is slightly confusing, but you guys have to memorize it, and eventually you'll learn it. Then comes the last topic, which is the operational efficiency implications. Okay. So this is where the density theory connects directly to your aircraft type. Suppose you're flying a piston or you're flying a jet engine. Now for low cruising altitudes like piston engine aircraft, efficiency is greater in high latitudes than in tropics. So tropics is somewhat mid 23.5 to 23.5 north to 23.5 south. These are the tropics. Now if you ask why, now because is denser, the air engines are able to breathe more, they can perform better, and the wings will produce more lift because the density is more. Okay, so that is the explanation for this. And then high cruising altitudes for jet aircraft. Now, like a jet aircraft, efficiency is greater in the tropics than in high latitudes. Now, why? Because the tropopause is higher, and the air structure will be different, and jets can cruise more efficiently at higher true altitudes. Okay, so always remember, density is not just about weather; it is also affecting your route planning, your aircraft selection, whether you have to fly a piston or a jet. Then maybe payload decisions, how much weight you have to carry, how much passengers you are allowed to carry, how much cargo you have to offload. Then it also affects your safety margins, which is very important for flying in a actually, because you're also having 200 passengers at your back. Then if you understand how density is changing with altitude, so basically it changes with altitude, it changes with temperature, with humidity, and also the diurnal activity, which is it, whether you're checking within the day or you are checking within the night. Then also the season comes into the play. Then also the latitude, as we saw, so it is moreover the dense areas, which is poles. Now that is it what makes you think like a professional pilot, not just a student who is preparing for your exam. Now we'll use these ideas again when we study performance, takeoff charts, and etc etc. So that is it for this. So we'll quickly mark this and we'll move to the MCQs. Now efficiency is greater in high latitudes than in tropics. Then, for high cruising altitudes, which are jet aircrafts, efficiency is greater in tropics than in high latitudes. So, that is it. Now, we'll move to the MCQs. So, these are the MCQs. Uh, you can do it all. Remember, read each and every question twice and check all the options first and then only mark your answers. Because what students come to me after doing these questions is they tell me that we are not getting the answer, and then if they do it again in front of me, they are getting the right answer, which means that they are not reading it correctly. So that is it for this chapter. So we'll quickly revise what we have studied. We'll take 2 minutes for revision. So, why is air density required? Because it is a critical factor which affects the air performance. Slower climb rates, like landing takeoff distances, and engine thrust is reduced, longer takeoff runs are required when it is low density. So, takeoff and landing distances are changed, and then all up weight calculations have to be adjusted, because if the runway is small and is if the runway is shorter and the aircraft is heavier and it is a sunny day on a summer afternoon, so you cannot take off on that. Then comes the atmospheric density, so defined as the mass of air contained. This is the unit. Then comes the density altitude, which you feel at the ISA. Then comes the ISA relationship, PA is equal to DA. Then comes the temperature deviation rule, which is 1 degree Celsius changes 120 feet change in the density altitude. If the temperature is more, density altitude will be more than the pressure altitude. Warmer atmosphere than ISA results in a higher density altitude. And operational impact is higher density altitude means takeoff and landing occurs at a higher effective altitude. Then comes the density of dry air. So fundamental gas equation comes. So for dry air, it is this. These are the names. Then comes the values, and you can find the answer on your own. Then comes the density of moist air. It obeys the gas law, and 8 is to 5 times that of the dry air. Then comes the total pressure of the moist air, P plus E. Then comes the density components. These are the values for the density for the water vapor and for the dry air. Then comes the final equation, which is the combination and the key takeaway. Then comes the factors. So altitude increases, density reduces, temperature increases, density reduces, humidity increases, density reduces. So if the humidity is high, you have to increase your takeoff distance by 10% and expect a reduced climb rate. Then comes the variation in surface density. The temperature dependence density is inversely proportional to the temperature in Kelvin. So warmer the air, lighter will be the density. Colder the air, heavier the density. Then comes the diurnal variation. Lowest density is in the afternoon. Highest density is just after sunrise. Then comes the seasonal variation. So due to changes in the season, there is change in temperature and pressure. Then comes the approximate density changes value. So 1 degree decrease in density is caused by these values. Then comes the variation of density with height. So density decreases with height at all levels. There is a chart which you can see. So for 1,000 feet, density reduced by 3% of the value at that level. and it is valid only up to 20,000 feet. Then comes the atmospheric extent. If the density remain constant, the atmosphere will end at 8 kilometers. These are the significant corresponding values according to the kilometers, height in kilometers. So 6 kilometer, 11, 17, half here, one fourth, and then one eighth. Now, even at 240 kilometers, there is enough density to resist the space aircrafts. Okay. Then remember the latitudinal variation. So at sea level, density is lower at equator and highest at poles, but only up to 8 kilometers. And after 8 kilometers, the density becomes higher as compared to the equator than at poles. Then comes the operational efficiency implications. So low cruising altitudes, which are basically used by the piston engine aircraft. So efficiency greater in high latitudes than in tropics. Then high cruising altitudes, efficiency is greater in tropics than in latitude. So what is the reason? This is the reason, which is latitudinal variation. So that is it for this chapter. You have also completed we have completed chapter 4. So in the next one we'll start with the humidity, and I hope you guys understood this. And if you have any doubt, you know the drill. Comment in the comment section, and your doubt will be solved. And till then, take care.